My name is Eldar, and today I'm going to talk about our recent paper called Mathador-LM, which stands for a dynamic benchmark for mathematical reasoning on large language models. This is a joint work with my colleague Amir and our supervisor Dan. So basically, there were a couple of things that motivated us to come up with this new benchmark. One of them is that LLMs started surpassing, or they've become very competitive to humans in many standard benchmarks that we're using these days. Then the performance saturation intensifies with model scaling. So this is something that we have seen happening very often. As we increase the model size, of course, accuracy goes up, but then at some point there seems to be like a saturation region where even with more scaling, we are starting to get diminishing returns in terms of the accuracy. And for example, the best achieved score on one of the popular mathematical benchmarks, GSM-8K, at the time of writing this is already 97%. Then one of the main problems that we are faced with these days, given pre-training data sets which have trillions of tokens, is like the test set leakage. Basically, I'm citing here findings from the paper from the last year, which showed that data sets like Red Pajama, Star Coder, the Stack, Flame Chain of Thought are all contaminated to varying degrees, anywhere from 0.5% to 19%. And then all of the benchmarks, like contemporary benchmarks that we are using these days, they're all static, and they lack they're not all, but most of them are static, and they lack difficulty control. So the static thing means that we create a benchmark with like a fixed set of question-answer pairs, and then once the models become very good at the benchmark, we kind of forget. We start using the newer versions, so we have to kind of recreate the benchmark from scratch again. And then we also lack the difficulty control on top of all of these static benchmarks, which means that once the models score very well on a specific task, there is no way for us to make the same data set a little bit harder, kind of to restart the game again. And then the existing decontamination techniques often fail to identify these problematic samples. So, and this has been shown in the paper that I'm citing here, which actually showed that by just taking the standard benchmarks, rephrasing them with like very simple approaches, like asking an LLM model just to rephrase test samples, almost all methods that we have these days for decontamination fail to identify these samples as the problematic ones, which means that most likely at scale, when we like scrape the entire web to create our pre-training data sets, we are most likely covering a lot of test samples that we shouldn't cover in order to get the fair evaluations. And here we try to summarize our findings in this plot. So kind of the state of things on three benchmarks like Mathador-LM, and then we use MMLU and GSM-8K as two popular benchmarks that we use very often these days. And then we look at the performance of three model families: Qwen2 instruct, Phi3 instruct, and Meta-Llama 3 instruct. And what we see here that we are looking at the accuracy versus the number of weights in a model on a log scale. And then what we see here on MMLU and GSM-8K is that as we increase the model size, the accuracy goes up. But then there is some point when we enter this saturation region, and as we can see, even with a more scaling the models even more will not give us like the same gains as it did with the smaller models. And then we also see that on most of these cases, we are getting very competitive against the human performance, which means that we ideally would like to have like some harder benchmarks to deal with in order to drive the development of both model architectures and the training data sets that we use. And then on Mathador-LM, we plot the same thing, but here we see that we are like very far from the human performance. More specifically, here we are looking at the performance relative to the average third grader in France last year. So that's the setup for which we have the human scores. And we see that even the best models are very far from that score. And then we are also very far from this saturation region. And here I'm just going to present a couple of examples just to materialize these kind of claims from the paper. That was one of the main motivations for us to come up with a new dynamic benchmark. Just kind of to show a couple of examples of what do they mean by contamination and decontamination. So here we see an example from Code Alpaca, where a human eval tests a sample. It asks like a model to write a Python function, which is going to sum up the numbers from 1 to n. But then in the Code Alpaca dataset, which we very often use for training of coding models, we can see exactly the same setup here, just like a implemented in a slightly different form, but it's a function that's doing literally the same thing. Then the other example is on the red pajama dataset, also like a test sample from human eval, which is just changing the base of model. And then in the red pajama dataset, training dataset, we actually see like a function that is doing exactly the same thing as the one from the test set, just in a slightly different way. Then the next interesting thing is the self-contamination. So basically the math dataset, which has been presented as a slightly harder version of the GSM-8K dataset, even has this kind of unfortunate thing where training and test samples are the same. They just have slightly different wording. So for example, here, the test sample from math asks like how many 3-digit positive integers are multiples of 11. And then in the same dataset, just in the training split, we have the same question, how many positive 3-digit numbers are divisible by 11? And then on the GSM-8K, also there were a couple of samples where training and test samples are asking the model to perform exactly the same set of steps and the same reasoning to arrive at the answer, but the numbers are just substituted. So as we can see here in this example here, the model has to use exactly the same steps to obtain the final result, except that now just the numbers are slightly different. So now we get to, so all of these were to say that like we wanted to come up with a benchmark that is a dynamic benchmark, which means that we can generate the instances of the test samples on the fly. And then whenever there is a new model that we want to evaluate, we can just generate a new set of fresh samples that model couldn't see before to evaluate it in the unbiased way. And here we have like the first definition, which we call like a formal definition, or definition for reviewers, which has like a little bit of these fancy notation. But in principle, it's a very, very simple game, which we'll cover in the next slide. So basically, we are given a set of operands A, which in this setup, we exactly follow the rules of the game that are imposed on humans, so that we have like a comparable scores against those. But most of these things can be changed a little bit, which we'll show a little bit later, so that we can extend the benchmark and future-proof it. So we are given a set of operands A, and we are given like 5 of these base operands. They're all positive integers, and we are given a target value T, which is also a positive integer. And then with P, we denote all possible permutations of this set of 5 base numbers or base operands. And then for each of these permutations, we also to these permutations, we assign them like the set of operators O, which is a set of the basic four basic operators of addition, multiplication, subtraction, and division. And with this PC notation, we just represent the set of all valid parenthesization of this expression. As you'll see later, some of these are not, like according to the rules of the game, some intermediate steps are not valid steps, so we have to exclude them. And then once we have all of these expressions that we can combine, that we can create with these five base numbers and these 4 operands, we for each of these expressions, we assign them a value E, which is literally computed by kind of just applying these four operators on these 5 operands, which literally means just kind of calculating the result of these operations. And our goal is now, given these expressions, our goal is to find the one that maximizes some specific score, which we'll define a little bit later. But we want to find one that gives us the best score under the constraint that the value of this expression is equal to this target number T that has been given to us. And then on top of this is the standard basic definition of the Mathador game. And on top of that, we just added one additional thing, which we call like a difficulty measure, so that we can control the difficulty of the benchmark and get a little bit more things to play with on the experimental side. And with the difficulty measure, we actually just try to represent like all possible target numbers to classify. We try to classify all target numbers into groups of, like, let's say, easy, medium, and hard target numbers, because some target numbers can be reached in many different ways. So with many different combinations of 5 base numbers and 4 operands. And some target numbers are much harder, and they can be reached in just a few different expressions. And then we assign this scoring function where we say that if the scores of these expressions are high, then the difficulty measure is high, because if the scores are high, that means the solution is a complex solution, as we will see later according to the scoring system. And then we also want to penalize based on the number of potential ways to reach the target number. If there is a lot of ways to reach the target number, then we consider this target number as an easy one. Whereas if there is just a few, then we want to consider that as a really hard target number to reach. And then the informal definition, or like the definition for humans, is as simple as this. So the game is literally like we have 5 base numbers, we have 4 basic operations, and then we have a target number. And the expected output is a set of arithmetic operations that we have to perform in order to reach the target number. And the main constraint that we have to follow is that each base number can be used only once. And how this looks in practice is literally like this. We get the target number, for example, 34. We get 5 base numbers, for example, 4, 2, 8, 11, and 17. And then we try to create a number 34 by performing the simple set of arithmetic operations with these base numbers. And then one simple solution to get 34 is to multiply 2 and 17. And this is a solution that gives us a score of 6. And then there's also another way to reach number 34, which is a much more complex way, which is turned in this way. In this setup, we call it like a Mathador solution, or the best solution. And this is the solution where we use every base number only once, and each operation from this set of basic operation only once. So we are not allowed to repeat the base numbers. We are not allowed to use the non-existing ones. We just have to move around these operators to recreate the target number. And this is the solution that scores the highest amount of points, in this case, 18 points. And this is the prompt that we use kind of to present the game to an LLM model that we are evaluating. So in the Mathador game, players use the given base numbers and the operations of addition, subtraction, multiplication, and division to reach a specified target number. So each use of addition is worth 1 point. Each use of multiplication is also worth 1 point. Subtraction is worth 2 points. Division 3 points. And then if a model reaches the target number by using all 5 base operands and all 4 operators exactly once, then this is called this Mathador, or the best solution, and it's awarded with additional 6 points because it's much more complex to find this solution relative to any other solution. And the main rules of the game state that in order to get any points, we have to reach a target number. We are not allowed to repeat the numbers, so we can use each base or intermediate number that we produce, like in these calculation steps, only once. And then we are also not allowed to produce like a non-positive numbers or non-integer numbers during the computational steps. And just kind of for easier like evaluation, we ask the model to present the solution in just 4 lines, which denote like these 4 steps that the model has taken to reach a target number. And then the scoring system looks something like this. So target number, if the target number is reached, we award that with 5 points. Addition is 1 point, multiplication is 1 point, subtraction 2 points, division 3 points, and then if the model reaches the best and the most complex solution, it gets 6 additional bonus points. And then all invalid solutions are all solutions that do not reach a target number, solutions that reuse numbers, you produce negative numbers, or produce non-integer numbers. In order to evaluate LLMs on this game, and to have like a setup which is comparable to human scores. We followed exactly the setup that was used last year in France, because in France there is a competition for students where they compete in this specific game called Mathador, and the rules of the game are that there are like 5 base numbers. First number is sampled uniformly at random from this range 1 to 4. Second number from the range 1 to 6. Third number from range 1 to 8. Fourth number 1 to 12, and fifth 1 to 20. And then we imposed these constraints, and then we evaluated all popular LLMs these days, ranging from the models from the Meta Llama 3 family, Qwen 2 family, Claude, GPT 3.5, GPT 4, Phi 3, Mistral, and a couple more which I haven't added to the plot here. But kind of all this to say that we found that none of these models are able to exceed a score of 14 or 15 points on the accuracy scale from 0 to 100, whereas the average third grader in France scored about 43.5 last year. So then we kind of, seeing these results, we spent quite a lot of time on playing with different prompting strategies, like trying to do some forms of chain of thought, presenting like a little bit more complex prompts to the models, because we thought that our prompting technique might not be the best suited one for LLMs. But after failing to find the ones, after like spending a lot of time on this, we decided to write a paper about this, and maybe someone else will figure out a better prompting approach than the one that we used in the paper. So then we, after we did these experiments, then we tried to figure out what's happening and why LLMs are not performing as well as they perform on other mathematical reasoning tasks like GSM 8K, math dataset, and so on. So then our kind of first investigation was with respect to the number of shots, because on all other tasks we have seen that adding like these kind of multiple examples in the prompt before asking the actual question to the model, we have seen that this would usually correlate with much higher accuracy, because the model gets to learn what is expected what's expected from it. But unfortunately, in this case, like we tried like changing the number of shots from 2 to 20, and we have seen that as we increase the number of shots, the accuracy goes up a bit, but then it starts plateauing at some point, and after 20 examples shown in the prompt, the models do not improve a lot. Then we tried to figure out why these models are performing really bad on the Mathador benchmark, and then we looked at the errors that they make. We classified the errors into 4 categories. The first group of errors are formatting errors. These are the errors where the models do not follow our instruction to present their kind of path to solution in at most 4 lines, and each line has to be like A plus B equals C. And as we can see here, like most models actually like follow the instructions very well, so they understand what they're supposed to do. Then we have the calculation errors. These are the errors that models make, like during performing the simple arithmetic operations, like A plus B equals C, but then the C is not the correct number for the expression A plus B. And we have seen this that for smaller models, it's on average around 20%. But then as we increase the size to 70 billion, we see that this drops, and it drops consistently, also like for Qwen models and like a larger Mistral models. So as we increase the model size, it seems that the models are able to do these basic mathematical operations. Then we have the third group of errors. These are the errors where models they actually missed the target number. So they followed our steps correctly. They did all operations correctly without making any mathematical errors. But unfortunately, the target number that they produced is different than the one that we asked for. And then the largest kind of like the largest fraction of these errors goes to the 4th category, which we call like illegal operand category. And this is the category where models actually start hallucinating. they invent numbers, or they come up with numbers that are not allowed, which is something that we have seen happens very often with these closed source models, where they try kind of to please the user. So they would really like to in the final step to give you the target number, but unfortunately, because of the previous set of steps, they made some mistakes. They used some numbers that they weren't supposed to use. So then they start inventing new numbers just kind of to get the final target number in the final step of the calculations. And then, because we saw that this is a major problem for all of these models, we tried to tackle it by injecting the set, by explicitly stating the set of allowed operands at each step. So the model would produce like A plus B equals C. Then we would inject like, okay, for the next set of steps, allowed operands are, and then we would give the set of allowed operands. But unfortunately, this did not change result at all. We thought that presenting the models with like explicitly stating what is allowed in the next step would help resolve this issue. But unfortunately, like the same problem appeared, where the models in the last step, they really would love to produce the target number. And then they start like hallucinating numbers, which they need to use to reach the target number. And then one additional and final kind of post-analysis that we did here was like related to this dynamic property of the Mathador benchmark. So basically, like a reliable benchmark must be a reproducible benchmark, and that's mostly the reason why like a lot of benchmarks we're using these days are static. Because if we evaluate a model today and evaluate it, and we evaluate the model 10 times, we want to get more or less the same results always, so that we can reproduce this. And this is one of the major problems with dynamic benchmarks, is that like it's very hard to get this stability in results. So given the different iterations of the test samples, we could get like different results. So we wanted to test this on Mathador as well. So here we can just focus now on the mixed difficulty ones. So we generated 5 groups of distinct test sets: one with 100 samples, one with 250, one with 500, one with 1K, and one with 1.5K. All with the mixed difficulty. And then we evaluated like a lot of models on this, and then we computed the average score across all of them. And we have seen that despite the fact that we are creating 5 different test data sets of different size, we are getting the accuracy numbers which are in a 1 standard deviation range of each other, which seems, I guess, suggests that the benchmark is pretty stable with respect to this. And then we also wanted to do a test to figure out whether our heuristic scoring function for the difficulty made any sense. So we generated like a 1K data set of really easy samples according to the difficulty measure that we defined. Then 1K of the medium ones, and then 1K of the hard samples. And we have seen that, at least kind of based on this simple difficulty measure, the results kind of scale accordingly. So the easy gets the highest accuracy across all models on average, and the hard one gets really bad scores, like three times worse than the easy ones. So at least given this, we have some control over the difficulty measure of the benchmark. So the main takeaways from this part is that the Mathador seems to be like a really hard benchmark for LLMs. Because state-of-the-art open and closed source models score below 15% on average, whereas the average third graders in 2023 scored around 43.7%. Then we, on top of this standard like a Mathador game, which we just kind of ported like to a programmable Python script, we introduced the notion of difficulty, which gives us the ability to make the benchmark a little bit more robust and future-proof, which means that once we get the models which are scoring really well on the benchmark, we can just kind of twist them up and increase the difficulty to kind of get them a little bit more challenging benchmark to play with like the better models. And then one of the most important factors is that the Mathador-LM has the property that model performance is stable across randomly generated problem instances of the same difficulty, which gives us this ability to evaluate new models with the fresh and dynamically generated test samples, and then therefore kind of preventing or reducing the probability of overfitting and the test set leakage into these huge pre-training data sets that we're using these days. And yeah, the link for the paper is here. Our code is available at this link, and the paper will be presented at EMNLP 2024 next month. So in case someone is coming there, yeah, we'll be there as well. Yeah. So if there are any questions, I think we can take them.